Hey, welcome back. We are wrapping up our computational mechanics winter course. I'm just checking, making sure our stream is actually recording things. It looks like the video is starting to come through. And our computational mechanics winter course, I'm just checking, looks like the audio is also coming in. Cool. All right. And the latest thing that we've been working on was homework 3, and today kind of working on project number 3. So main thing that I saw in this first problem was some people maybe were using like AI to figure out like how to do this, but the AI is just going to generate random data. It's not actually going to walk you through the reading. So make sure like you can, anytime these homework are there, there's links to the reading, like directly connected to those problems. And so you have to go through this reading and actually analyze the motion, the projectile motion of this falling object. Let me see if I have anything saved in here. No, I don't have any. So I won't walk through this whole thing because you can read it on your own. But main thing is that we are coming up here. Let me just run through some of these. There's a video of like a ball falling forward and then a ball just falling. So they're both released at the same time. One is rolling forward, the other one's falling straight down. We want to capture the motion of that forward motion. So the first thing is you have to gather the distance between all these horizontal lines. So every 10 centimeters you click along there. That gives you this, coming down here, this gap lines. So once you figure out like what the average distance between each of those things is, and you take the average because there's always a little bit of error as you try to click on the images. Now you have that, 10 centimeters is, let's say, 56 pixels or 61.8 pixels, something like that. So then we can use that to actually convert the coordinates that we start clicking on as we track the ball and convert it into meters or centimeters, whatever you want to do. Okay, so I wanted to talk about that because it seemed like if you just grab this and tell AI, actually, why don't we just try that? Let's see where AI, learn about the topic, and so I think if we just tell it to do this, it tells us that acceleration is 2 times that first constant. That part is correct. And let's see. Oh, so it is telling you to load those coordinates in. But if all you're doing is like copying and pasting this this work into here, so let's paste that in. It's going to tell you that there's nothing there. So then I'm like, oh, okay, well, let me just tell Copilot I received this error. And now it's probably going to, oh, that's why people were running this code. I was wondering where this came from. It's because some people were like importing OS and listing the directories when it's like, we've already looked at how to do that. You would say ls, like bang ls, and that would show you what's in there. The os dot list directory, that works. Where did you save the file? Yep. Okay, yeah, so that's where that was coming from. But I think if you keep pushing it, it's just going to make up some data of like, okay, here's what is it? Search the entire workspace. I don't think this one's gonna help, because if you're listing everything from here onwards, we would have to list everything from the home directory, and then it would start showing you stuff. Anyway, okay. So that answers like where that os dot something came from. But this thing, you got to go through the actual like clicking through the video to figure that out. This one, I saw some interesting approaches to this falling tennis ball example. And actually, this one I wanted to try in here too, because a lot of people were trying to use like manually create a window to actually figure out where the peaks were, like where the min and max were along the line. So let's just see what this thing is telling us. And part of this is just me kind of learning like what's current capabilities of AI. AI does great at things that have been solved 1,000 times. This one is not like a brand new problem. It comes up pretty often. All right, so we load this, then we compute the derivative, and that's fine. That's what I would do. And then we plot it. And all right, so maybe this is where slicing is starting. dvy, okay. And then I don't know why appending is such a popular thing for code, because it's an awkward way. If you're just like doing a for loop like this, you're not really sure if the number of e-values is going to match the number of items in your list. So I don't like to use append unless I'm just trying to like be lazy and just run it real quick. Let's see. Oh, so it puts it all together here. Okay. So let's see. Yeah, and it didn't work. So in collision 1, negative 2.5 is somewhere around here. And negative 1 point. It doesn't even make sense that the velocity before impact would be that they would both be moving in the same direction. So like the coefficient of restitution is just talking about like almost an acceleration, like a relative acceleration or something. Let's see. So this is the main part of like these slices. So if I was trying to do this and I wanted to use, like if I thought that this method is the best method, I don't think it is, but it should work. We can shoehorn it and get it to work. There's no reason to plot. If I'm going to use indices like this, then there's no reason to use time on this x-axis for this plot. So let's, instead of plotting t comma v, we can just plot like vy, and now I have 0 through 2500, because that's how many data points I have. So it starts off at 0 speed, goes down to like -5-ish, about -5, bounces, goes back to +4, then -4, +3. So roughly I should be looking at something that's like 4/5. That should be my collision, just based on this graph, just without doing any real math. So my slices should be like 0 to 1,000, 1,000 to, I don't know, 1,500, something like that, and then maybe 1,500 to 2,000. I don't know. So let's get rid of this. We'll say 0 and 1,000. And let's see if that even works for at least the first one. So at least it worked for this first one, right? I don't love I don't love this for loop. I don't know why it's making it so complicated. V min, V max. I mean, like, why isn't this what I'm after? Why am I going through this whole thing? But whatever. Yeah. So it worked in that case. Then the next impact should be about 1,000 to call it 1,700 or 1,700. Then the last one should be, I mean, really 2,000 to 2,500. Because impact happens somewhere in there. Now, at least I'm getting the same, it should be the same coefficient of restitution, because it's the same ball bouncing on the same surface. It shouldn't change all that much. I don't know why this thing is using 2 sets of for loops for these impact slices and all this. Like, why not just dump all this into this thing? It just feels unnecessarily complicated. So right now, and yeah, I don't need any of this because I'm already importing that up here. Like, it's the very first line that I import. And yeah, same thing here. It drives me crazy. Like, why import it over and over? So if I'm grabbing this code using AI to run it, then like I need some kind of information, because if I'm trying to help troubleshoot, like, so here as I'm like critiquing and trying to understand like where errors come from or like why things aren't working, I need to know, like, is this computer generated code or is this human generated code? Because there's a very different thought process. Like, this AI is kind of an autocomplete of just like, here, this is the general thing that I want to do, and then it's just sort of grabbing random bits of code to throw into problems that are similar to that. Sometimes it works great. Other times, like this time, I had to go in and troubleshoot it, but I want to know, like, was it your choice to make 2 separate for loops and like create these slices? Like, how did you get those slice numbers? Because the AI doesn't know. It's not looking at the graph. It can't tell what's happening. It's just and again, it's randomly generating. And when I say it's random, like, it actually is random. It has a parameter called temperature. They call it temperature because it's kind of modeling like entropy in the AI algorithm. And if the temperature is like, I think normally for Copilot, I don't think you can change temperature here. Maybe not. But other, like if you use Olama or other AI systems, the temperature is a value that you can change. If it's 0, then there's no uncertainty, like there's no randomness at all. And if you say the cat jumped, it will always tell you into a tree or something, or whatever the most likely thing to say. If you put the temperature up at 100, then it's almost going to feel like a fever dream of like the cat jumped, and then it might go off on a tangent of like with a crab to the rabbit's house or something. Like, it might syntactically make sense because it does try to match grammar correctly based on rules that it's sort of created math around. But anyway, that was a long explanation of, if you're using AI, I gotta know like what, like something in here. Generated code from Copilot with prompt. Oop. And I'm trying to. Let's see, where did I? So it gave me a lot of information, even though all I said was. I mean, here it is the question prompt. I didn't even do prompt engineering, right? Like I'm really shortcutting this system. Like ideally you have like a little, if you're gonna be using AI, like do a little more prompt engineering than I'm doing, because this is just hoping that things kind of work out. But at least now I know it came from Copilot. The prompt was this question, and like if you have questions about it, or like usually I have questions about it of like, why are you doing it this way? Okay, anyway. All right, and then integrating fall drag seemed to work. This one, so this is technically a typo, but you could leave this as, so this was one thing that kind of came up. So if I say G over L times cosine of theta, like that, pendulum of, if I look at pendulum at moving 0 radians per second, sorry, it's at 0 radians, so 0 degrees, and it's moving 0 radians per second, its acceleration is negative 9.81. Because really what I said here when I said that acceleration is cosine theta is whenever it's horizontal, theta is 0. And then from there, this is an oscillating system, so we need some kind of like oscillating. We can either use really small Euler time steps, or we could use one of the better, like higher order methods that we have here. So I'm gonna come down spring mass. We could use this Euler Cromer. That one works just fine. And again, it just helps to watch. It helps to think about how systems get integrated. So I'll just go from scratch. I'm not going to ask Copilot to do this for me, but I'm going to initialize my variables and then start solving one by one. Okay, so step 1, time is my independent variable. I can set up time for as long or as short as I want. So I'm going to say that it's linspace from 0 to 2 times pi divided by omega, which means I need to define what that omega is, where w is square root, if I could spell, of G over L. So the natural frequency of this pendulum is square root G over L. Now I need to define what my state is. In this case, I want for every step in time from 0 to, and I want 2 oscillations. So let's say 4 pi. So from 0 to 4 pi, and let's give it 51 steps. So this will be 51 rows long, and I need to save both the the angle, the radians, and I need to save the radians per second, so how fast it's moving. Then I know that state 0 is pi over 6. And state and then the speed is 0. Now I need to step through state 1, 2, 3 all the way up to 51 based on what my initial state is. For I in range 1 through length of t. So going from 1 to 51, my state of I is 1 Euler-Kromer step. So I can look at, I'll just grab this. So I'm going to use my previous state, because what this function does is that if I give it a state and I give it a function to define what the differential equation is, and I give it a time step, it'll tell me what the next state is. So let's try that out here. So I can say 0, 0, and then my right hand side is pendulum, and my, let's say 0.1 seconds. And what it did was it took that 9.81, multiplied it by 0.1, and now I'm moving at almost 1 radian per second in the negative, so in the negative direction, so downward. So yeah, I gave it acceleration, the velocity acceleration, and current position velocity. Then it told me the next position velocity. My right hand side is going to be my pendulum. My dt, I should define it. And let's just run that. Oh, g is not defined. That would help. Nothing happened because all I did was create the state, but I do have values for 0 to 4 pi over omega. So let's take a look at, we'll just run that. We'll plot t and state colon comma 0. And what I can see is that I start at pi over 6 and then swing down to, really this is like negative 90 and then negative 90 plus pi over 6. So if I want a full 2 oscillations, because now I'm looking at nonlinear pendulum behavior, I need to increase this. So roughly I have 1.5, so let's multiply this by like 1.5, so 2 over 1.5. Is that gonna work? Almost, yeah. So maybe I had like 1.4. Pretty close, right? So maybe I had 1.3 oscillation. 1.1? Oh, I'm moving the opposite way. And so 45. There we go, pretty close. And what I was doing was just, I wanted two full oscillations, and I knew that I only had like 1.4 or 1.5. So it went to here, so I wanted to make it a little bit longer. Other option is say like, no, I don't want to define this as cosine theta. I want to use that sine theta, and then it's easier to find that the 2 oscillations like this. But it takes a little bit longer if you have bigger swings, because we can see the oscillation, it's slower. we don't have a small angle oscillation anymore. Cool. And then what are the other things? One thing that came up in so it seemed like people were able to like look at let me run this one, restart run all. And then I'm going to go back up to, so this was the modified Euler's method. It had an order 2 convergence. It seemed like most people were able to kind of recreate this plot using this starter code where we looked at that modified Euler, like this RK2 step. So I won't go through that. There's a couple examples of what this convergence plot is, and these are really helpful in terms of like a meta-analysis of like, is this the right integration method for what we're trying to do? And if we go through and use like a solve IVP, like the initial value problem solvers from Python, you don't really need this because each method is going to have a given convergence rate. So an Euler method is always a slope of 1 on this log-log scale. These second order methods are always a slope of 2. So the error, if you have 10 times smaller time step, then you have 100 times less error. So it converges faster. Higher order, and most of the solve IVP, like the Python integration methods, they use fourth and fifth order, like fourth order and second order convergence. So you don't have to worry about this as much. And then it also uses variable time steps. So you don't have to have a fixed time step for every point in time when there's not much things that are interesting happening in your differential equation. Again, it's good to see it and understand like why these things are doing that, or at least get some experience of like what is integration, how does it work, and that kind of stuff. So then, yeah, let's try this one, because there's two things that come up here. So let's do this, and let's just say derivs equals zeros of state, and then I guess I didn't really need that since I'm making an array anyway. Let's see if this one works. V is not defined. That would help, huh? XV equals state. Zeta is not defined. Zero 0.2, W equals 2. Okay, cool. So now I've got, if I give it position, velocity, it'll tell me what the velocity and acceleration are. All right, sounds good to me. So now what I'm going to do is grab the actual code for Euler, Runge-Kutta, and Hyun from the reading, rather than having AI generate it, because I don't know exactly where AI is grabbing that code from. And we already have them defined in the reading. So if I do a quick search for Euler, here's my Euler step. I can grab this one and paste it in here. So now I have an Euler step. If I do a search for Kuhn step, and let me copy this and then I'll talk about it in a second. And then do another search for RK2. And let's do step, here we go. Okay, one of these methods is not like the other. Euler step, we've seen this one before. Take the current state, add the derivative, multiply by time step. That one we've used over and over now. Runge-Kutta step, we're taking like a midpoint, so calculating what the mid state is and using that to calculate a new value for how much we want to step. And then I saw some people, I think they were grabbing some AI generated like Runge-Kutta methods. There's all sorts of higher order methods where you might calculate 4 or 5 different mid states to calculate the next state, and that would be like a Runge-Kutta 4-5 kind of method. So this Kuhn step, this is the main thing that makes it an implicit method. There's something in the code that says don't move on to the next state, like don't give me the next state unless you actually do something to check that as I'm trying this like mid-state calculation, that it's not changing, like I have the right number. So there's some kind of iterative correction inside of an implicit method. AI for some reason uses like an fsolve or something, but normally this is what you would see inside these codes, is that there's some kind of, it's either a for loop or a while loop, and there's some kind of tolerance where you have to reach that tolerance before you move on to the next step. So that's what this Kuhn step is supposed to do. That's what the implicit methods are supposed to do. Okay, so now, again, repetition is the key to learning. So let's set up our so we're going to go from 0 to 3 times, or I guess 6, because, well, I'll just say 3 times 2 times pi over w. And I define w inside my function, but I just want to grab it from here. So w equals 2. And then I'm going to call it like y Euler, y Kuhn, and y RK2. And all those are equal to zeros, which is the length of t, and 2 values. Let's grab all this. And I want to set up the initial values. And then this initial value, what did we call it? We said, it doesn't really matter what the initial values are, but I can't, for 2 and 0, we could use that, 2 and 0. So 2, 0. And I didn't actually specify what this is, so let's call it like 101 to start. And now I'm gonna paste in these, and I'll just write out the Euler step first because I want to say that it's the y Euler. Well, I'll just leave it as y. And then the right hand side is my SMD, and my time step is dt. And instead of Euler step, I'm going to write Hune. And then down here, I'll say that this is the RK2 step and RK2. And this one should be Euler. And instead of 0, right, this should say I. And then this one should say I minus Euler step is not defined. It would help. Oh, there's no underscore? That's annoying. I want it to have the underscore. Make it all the same. That would drive me crazy. Oh, I'm missing a negative sign. How do I know that? So I started off at 2 meters, and then as I'm bouncing, I'm growing. So instead of an exponential decay, I'm looking at an exponential growth. Euler method, probably there's something wrong with Euler method. Time steps are too large for it. But even my Runge-Kutta and Hune methods, they shouldn't have growing amplitudes. So let's come back up. Maybe you noticed this as I was typing it and like kind of grabbing things. Okay, that should be a negative zeta. So in here, negative zeta. Try that. There we go. Okay. In this plot for, let's do plt dot title. Didn't like that part. There we go. And let's use colon 1.3f. So when I have 0.094 seconds, it works, but Euler method is not converged. It doesn't agree with these other two methods. So let's try, instead of 101, let's try like 51. Now Euler method is really growing. So let's say my y limb has to be 2 to negative 2. Well, let's go 2.1. Now I can see there's a little bit of disagreement, so I backed off too far. Roughly these two methods, the Hune and Runge-Kutta, should give me the same. If they're both converged, they're both converged. Like they should give me the same answer. And now they're starting to kind of look the same. And what I'm trying to get here, let's merge these two. So when I run it, it just runs. CV. So now I have two copies of it. One where these two are converged. Really, I would want to put, like, if I'm trying to turn this in to demonstrate that it worked, I would want to put a label and a legend in here, but you've done that, you know how to do that. Or you can ask for help from a Copilot or something. So here, even at 0.1 seconds, it seems like it's kind of converging. Meanwhile, if I'm trying to get Euler to the same spot, like where it's about the same, I need it to be 0.01 seconds. So another 10 times less. And then at that point, all three methods are converged. So it's overkill to use 0.01 second steps for these two methods, but that's minimum, or that's the max size for Euler step to even to get into that realm. So this is what I was looking for in this problem of, like, okay, when do these different methods all agree? Like, when are they saying the same thing? You can compare it. This has an analytical solution, like you can solve it and plot the actual solution, or even look at the error between these methods and kind of look at when. But yeah, so how does everything kind of converge there? So this one, all right, this I'm gonna grab this because this was driving me crazy as I was looking at some of the answers. So let's just paste it in there, and because this df/dt, I swear it's not giving the right answer for the derivative of this function. And I think it was AI. Maybe everybody. Maybe there were a lot of people that were doing derivatives incorrectly. But let's see if this thing gives the wrong answer that I was looking for. Oh my god. Okay, so there's my df/dt. Yeah, this doesn't look right to me. Like, I really don't think this is the right derivative. Let's go in there and check. Yeah, maybe. It really looks wrong to me that it's a times s times 1 over s, because I swear there's. So how's this thing doing it? We're taking df/dt. Where's z d sigma dz sigma one minus z? Why is that? I'm not following the logic of this derivative, but maybe I'm just not, like, thinking about it. Because if we have this function that is a 1 over this, like 1 over this function, then we should end up with a 1 over that function squared. So I don't know why it just gets to ignore that. Like there's got to be a 1 over something squared in here, because this thing, and so I'm kind of nitpicking this. I'm not going into too much detail about why I'm thinking this way, but this is one of the examples where AI is very good at grabbing things that seem like they're true, but it's not actually doing the math. It's just like throwing equations in there that it thinks are the right math. So I don't trust this different. It kind of looks right, because it does go from t comma f, let's just say like sigma of t. So when the derivative starts to become negative, and then it's the maximum right here, and then it starts becoming less, and then back to 0, it doesn't look too wrong, but it doesn't feel right. Like something's wrong. It does. I don't know where this came from. But again, I'm not digging too far into it. But anyway, I made a note on a lot of people of like, I think this derivative is not giving you what you want. But maybe it is. I don't know. Maybe it's close enough. And for Newton-Raphson is pretty robust. Like if you have a derivative that's not perfect, but it's getting you pretty close to the right derivative, it'll still get you to the right answer. And so people in this question about like why does this fail? Like what, and here, let's grab that Newton-Raphson method. Control F, Newton-Raph. Gonna grab this and pop it into my homework. Newt-Raph of, so the things that I need are the function, which is f t. I need my df dt. Then I need an initial guess. These this es is some error, like the desired relative error, and then max iterations. It shouldn't go to 50 iterations. If it does, something is wrong. That means that it's not converging. Okay, so initial guess, let's say it's 0. And this one, I end up with not a numbers, and then it went up to, well, when I said 50, like it shouldn't go to 49 is the main thing. So that one, it doesn't work, which makes sense because the derivative here is 0. And if I'm using this change in x as like take the function, divide by derivative of the function, and the derivative is 0, immediately it's not a real number. And even if it is a real number, even if this is not quite 0, like maybe it's just very small, it's going to take this and draw a line to look for where it's crossing 0. Not that, Control Z. So it's going to take the slope here and the position and try to find this 0, and let's f sub t. It's looking for this value, but it's trying to draw a straight line, so it's going to go way over here, and then it's even further from the result, and then it's going to go way over there, even further. So it'll just keep diverging. So I need something, and some people thought the takeaway was like, oh, if you're too far from this 0, it's not going to work. But that's not really true. If you're looking for the 0 of a linear equation, it'll converge in one step. Like even if you're billions off, it'll converge. If it has a constant slope, it'll converge in one step. Okay, so 0 doesn't work. So let's try more like 50, because 50 is here. Seem like maybe that'll get us closer. But 50 still doesn't work, because at that point, the slope here is going to guess that the derivative is out here. And then that one leads us back into that same diverging answer. So I need to be a little closer. Definitely like 60 degrees should work. If I say that it's 60F, then it quickly, within 4 steps, is already at that 0. This derivative really seems wrong, because it should be, at this point, it should be like 1 or 2 steps, and we should hit that error. But again, it's pretty robust. And this is the main check, is like plot the derivative. Like, since you have a function with the derivative, you might as well plot it and see. So we could back off to like maybe 58. Does that one work? Seems to work fine. 55. 55 doesn't work. And then it's probably about the same, like if I guessed 68, something like that. That should work. And then 72 works, 75 starts to not work. So at that point, we're over here. Like once we start crossing into this diverging area, then we don't see. Okay, last thing, and I'll just go through this real quickly. This shooting method is describing using, so this is showing like bounce number 1, and then what we're trying to do is predict the motion of bounce number 2 using this fall drag equation. So it's a few different steps. This one uses Runge-Kutta. You can use any integration method you want. The main thing is that we're going to define, let's zoom in. No, not that. There we go. Shooting method, defining problem. So we're defining a problem where the last height and the actual and the real last height and the calculated last height, that's what we're going to call error. So if that error is 0, then we chose the right initial velocity. That's that's why it's called the shooting method, because it's kind of like, all right, how do I create an initial slope such that the final value is what I want? So you can grab the code like right from here and copy it in. The main difference is, instead of looking at this time step to that time step, we're looking from here to there. And when you're done, try taking this speed that you get and plug it into this plot to see, does it match that last hump? And that's the best way to figure out, like, is this the right velocity to choose? Okay, that's all I had for today. Thanks so much. Keep up the great work. I'll take a look at project number 3, and then we'll wrap up with module 4. Okay, see you next time.